So welcome everyone. Today I hope to give a kind of accessible exposition to what the field of many-body quantum optics is really about. Maybe before getting into the talk, I'd like to actually just start with a poll. Okay, so the question is, you can vote for the most exciting quantum platform, and exciting you can define however you want. So let me just set two ground rules. Just to make sure we get enough statistics, each person can vote for, let's say, 2 systems if they want. And then people who are working in many-body quantum optics as their primary field, they can't vote because obviously that's a kind of big bias. Okay. So the first system is ion traps. Who's really excited about ion traps? 1, 2, 3, 4, 5. Okay, more or less. All right. Who's really excited about superconducting qubits? 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay, so superconducting qubits is in the lead. Rydberg atom arrays. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Atom light interfaces. So this could be Kavli QED or atomic ensembles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Okay, so actually, the poll didn't go the way I thought it would. I thought that atom light interfaces would honestly have come in last. Honestly, if I was voting, so I work in quantum optics and atom light interfaces, if I voted, I would not have voted for atom light interfaces, honestly. And in some sense, so the fact that you find atom light interfaces exciting, well, that's great to hear. I'm really glad to hear that. But actually, so the point of this talk was to actually try to answer at least why I wouldn't vote for atom light interfaces now, and what we can do to change that. And that last question, what we can do to change that, I think that to me is really this point of this many-body quantum optics program. So what can we do so that one day maybe everyone votes for option 4? Okay. All right, so why don't I, so if you ask me why honestly would I have voted for another system, I think just in terms of what's been demonstrated in these other systems, so far they're clearly on a for me they're clearly on a very exciting trajectory, where the experiments that they're doing, can start to access just really kind of unexplored questions, new phenomena, really discovering new phenomena, sometimes exploring strongly correlated phenomena, also kind of exploring the interface of, let's say, many-body physics and quantum information, and so on. And to me, atom light interfaces haven't really kind of caught on, to that trajectory yet. And so, maybe now, given that kind of, so that's my kind of honest opinion. And maybe now I'd like to kind of use that to set the context of what this talk is going to be about. Okay, so maybe there's kind of 3 main questions I'd like to address today. So first, what are atom light interfaces potentially good for? So we asked this question. I don't think there's really any doubt that these systems can be exciting. The second is what's the problem? Okay. So of course this is very kind of dependent on what people are interested in, but I would say kind of generally, maybe it's fair to say that there's still a kind of gap between what people would like to do with these systems and what people actually have done, especially experimentally. And then the third is what can we do about that? So the first two questions are meant to kind of get everyone up to speed, get a kind of whirlwind introduction to quantum optics, especially those who aren't experts in the field. And then, starting with that context, I'll try to answer or partly address the third question, which to me is really the goal of this KITP program. I should also say that the words many-body and quantum optics are so broad that if you ask 10 people in this program to give this talk, you'll get 10 completely different talks. So obviously, what I'm going to present here is my kind of personal version of it. I hope that the ideas that I'll state will resonate with enough people in the community to make it kind of rather general. But I hope that if you don't hear your favorite topic covered, it's not that I'm trying to kind of purposely exclude or diminish any particular idea. Okay. In any case, so it's a personal view, but it's also kind of again personally why I feel really excited about this topic of many-body quantum optics and about this program. Right. Okay, so let's maybe start with the first question: what are these systems good for? So I think first, just to be able to answer this, I should make sure that I kind of practically define for everyone, especially those who don't work in the field, what an atom is, or a minimal definition of an atom, from the standpoint of atom-light interactions. Okay, so for the most part, when I say atom, I'll really only have in mind its kind of electronic levels as the relevant degrees of freedom. So we can draw a kind of energy scale here. An atom, any atom will have some electronic ground state. If you think kind of hydrogen atom, this would be something like the 1s level. There will be some first, excited state. This could be something like, the 2p if you think of hydrogen. And the point is that these wave functions have different parities, which then allows incoming light to couple to them. So if I send a kind of classical light or coherent state light, like a laser, actually can kind of drive a transition from the ground to excited state. And of course, so when I choose this laser to be resonant with this transition, there are kind of other levels, there's an infinite set of levels in principle. They're even higher. But the thing about a hydrogen atom or any other atom is it has a very anharmonic spectrum. Okay? So unless I just go and like kind of blast this atom, this light that I send in, which is near resonant with this first transition, doesn't really care about any higher up transitions. So our definition of an atom, for practical purposes, is a kind of two-level system, or a qubit. And the kind of cool thing about this very simple system is, if I really just kind of do this experiment, I can go up to the excited state. But then, because it's a two-level system, when this thing drops back down by emitting light, it's going to emit one quantized photon. And that one photon, a single photon, is already a non-classical state of light. So this is kind of, in principle, could be a useful resource. So you see that a single atom, our atomic systems allow you to naturally generate non-classical light, which could be a useful resource in many different applications. Just to name a few, you might have heard of linear optics, quantum computing, boson sampling, etc. Another thing that atoms are good for is maybe nonlinear optics. At the level of single photons. So by nonlinear optical devices, you can think of things like optical switches, all optical switching, maybe all optical transistor. But then kind of at the level of single photons means that maybe you can kind of achieve kind of a transistor action or switching, or maybe even a photon-photon gate, at the level of sending in 1 and 2 photons. And to kind of give you a cartoon picture of how this might work, again, the magic is that an atom is a two-level system. So you can imagine I build a system or a device where somehow I shine in one photon, and then by kind of quantum optics tricks, I guarantee that that one photon, if it's on resonance, will get kind of reflected backward. Okay, so a single photon blocks, or sorry, a single atom blocks the propagation of a single photon. But then because my atom can really only support one excitation at a time, if I try to send in two photons at the same time, obviously, the atom can't reflect them both. So these two photons would tend to get transmitted. So this is a kind of simple example that already tells you that a single atom sees one photon versus two very differently. It has two very different optical responses. A third example. Here's a quantum memory for light. So light or photons is probably the best way to send quantum information over long distances. So a photon is a very nice kind of flying qubit. But then if you want to kind of process the information or store it, you can't have just your information always flying around at the speed of light. You just want to be kind of physically sitting in one place. And atoms are very good at that. You can design kind of protocols, reversible or unitary evolutions, that coherently map the wave function of a photon onto some kind of collective atomic excitation. So this photon somehow gets coherently and reversibly absorbed by, let's say, atomic gas. Another thing atoms are good for is metrology or sensing. Just to give a kind of cartoon picture of how that might work. So imagine I have ground and excited state, and then I can come in with some kind of maybe this atom sees some time-dependent magnetic field. That magnetic field could kind of shake this transition energy up and down, and then if I try to shine in light to probe that change in transition, that kind of time-varying field will somehow get mapped onto how photons come out. Okay, so if I can measure how the photons come out, I could try to infer what the effect was of the magnetic field on the atom. Okay, so this would be something like magnetometry. You can actually do better. So before you kind of do this, you can actually have a collection of atoms. You can maybe shine in light in the first place to actually entangle the atoms into a metrologically useful state, like a spin-squeezed state, and then kind of beat standard quantum limits when it comes to detecting things like magnetic fields, etc. And then the last thing, which I'll kind of just leave vague for the moment, is we have lots of degrees of freedom. So the number of photons in the universe is not a limited resource. Neither is the number of atoms. Okay, so you might ask, well, if I just have a lot of atoms in light, is there maybe the potential to see interesting many-body physics? Okay, so hopefully it doesn't take much convincing, to see that these kind of applications are worthwhile or potentially important. So I don't think we can really argue that atom-light interfaces are irrelevant. But now I'd like to get to the second issue, which is what is the problem? So I think the general problem is that so all these things that I've listed here, people have done experiments already, at least as kind of proof of principle at proof of principle levels. But again, without trying to overgeneralize, I think it's for the most part fair to say that how well these experiments work isn't really kind of how well we want them to work as a general trend. So let me kind of explain why that is. So what's the challenge? So kind of intuitively, if we wanted all these, so if we could somehow achieve a 100% efficient atom-light interaction, so free of errors, it kind of makes sense that we can start doing all these things perfectly. Okay, so in some sense, the bottleneck is just how well can we actually implement an atom-photon interaction. So let me try to just argue in a cartoon picture what the issue is in that sense. So one way to kind of characterize efficiency is just at the level of basic building blocks. I have one atom and one photon. So for example, I could say that I have some kind of Gaussian beam that I can create in the lab. I can focus that Gaussian beam down to some area, which is given by the beam weight squared. And then let's suppose that I can trap a single atom in the focal point of this beam. And then you can ask, well, if I have a single photon that's propagating within this kind of Gaussian mode, what's the probability that this photon will actually kind of excite the atom in the first place, as opposed to just kind of like flying by without knowing that the atom is there, and then kind of scattering that photon into some other direction. So what's the probability of scattering? So that's a perfectly valid way to define efficiency of atom-photon interactions. There's actually another kind of nice way, or complementary way. So you can argue, let's say either by reciprocity or time reversal symmetry, that you can also kind of try to characterize efficiency by kind of playing this movie in reverse. Okay? So in particular, imagine I had a single atom, and this atom, I just prepared it to be excited at t equals 0. Okay? So this thing is going to emit a photon. And then you can ask, what's the probability that it'll actually kind of collect that photon into a nice, let's say, Gaussian mode, which I can actually create in the lab. And the problem is really just that of kind of mode overlaps. So the problem is that, a kind of point dipole wants to emit a kind of low radiation pattern. And more or less, that natural emission pattern of the atom covers a solid angle of 4 pi. Okay? Whereas any kind of realistic Gaussian beam that I can generate here is not going to cover 4 pi. It's going to cover a solid angle proportional to the wavelength squared over the beam waist squared. And so then basically the interaction efficiency I can also just think of as the kind of like the mode overlap or the ratio between this solid angle covered by the Gaussian beam and this kind of 4 pi. And so then I conclude that the scattering efficiency, which is the same as this kind of collection efficiency, that goes like lambda squared over the area of the beam. And then when you put in real factors of 2 pi's and so on, the issue is that you have a diffraction limit, so you can't just kind of focus light arbitrarily. And if you literally try to build this experiment, which some people do, I think the state of the art of this kind of probability is around a few percent. And that's a challenge because again I said I want 100% and not a few. Okay? So that's a well-known problem. Okay, and of course people have had a lot of time to try and address this issue. So there are some kind of common approaches to try and fix this. And I'm sure you've at least heard of these approaches in name. So one is pretty simple. Instead of just having a photon like fly by once, I'm going to try to make the photon hit the atom over and over again, and that's the field of Kavli QED. So I kind of confine this Gaussian mode with 2 very highly reflecting mirrors. Put an atom here, and then my kind of interaction efficiency becomes lambda squared divided by the area of the beam. So that's a single pass efficiency times the number of round trips that I can make between the Kavli mirrors. And then kind of, quantum optics jargon, we have fancy words for this. This is known as the Kavli cooperativity, if you've ever heard of that word. Another approach is you can still work in free space, but instead of having one atom, you just put in many atoms. And then your interaction kind of naively gets enhanced by the number of atoms that you put in. And this object here is known as the optical depth of your atomic medium. So clearly, if this number of round trips or number of atoms is big enough, then these probabilities can be bigger than 1. So they don't really make sense as a probability anymore. But they still make sense in this kind of picture here. You can really think of it as kind of branching ratios. If I start with one atom which is excited, these numbers here dictate basically the branching ratio in which the atom could possibly kind of emit into this nice Gaussian mode, versus that I lose that excitation because it emitted into 4 pi. Okay, and once you view it as this kind of branching ratio of information, then it kind of makes sense that these numbers dictate the error of, or limit the error of basically any application that you want to carry out with atoms and light. And the point is that these numbers are limited in real life. Okay, so clearly you can't make mirrors that are 100% reflecting. Mirrors have a finite, absorption or scattering probability. You wouldn't necessarily think that the number of atoms is a limited resource. So why don't I just take all the atoms in the universe and build a quantum memory? The problem with that is, it's just kind of technically hard. Okay, so here what I'm giving is kind of fundamental, fundamental errors. But just kind of heuristically, if you try to work with too many atoms, at some point, indeed the kind of efficiency of whatever you want to carry out might get better, but then at some point, it can saturate or even get worse again. Okay. So, of course, to talk about, what are the limitations and so on is a little bit technical. But let me just kind of give a couple of kind of real-life numbers for you to get a sense. So if we look at kind of state-of-the-art quantum memories, so we really prepare a photon qubit and try to store it into an atomic ensemble. The state-of-the-art errors are about 10%. If I try to build a photon-photon gate, the state-of-the-art error is actually over 50%. Okay. And of course, when you look at these numbers, to me, that's the big difference between an atom-light interface and these systems here. Okay, so these systems routinely achieve entangling gates with errors of 1% or less. And the best entangling gate we have here, which is our deterministic gate, has an error of over 50%. Okay, so to me, that really kind of encapsulates really well what the kind of challenge is. Okay, so So to me, the point of this kind of many-body quantum optics program is not to just kind of look at these numbers and be sad about it, but to really ask, what can we do? Okay, so is there some kind of new way forward? So it turns out that there is, or I think that I and others in the field think that there is. But first, to explain that, maybe I should point out a subtle kind of physics hole in what I told you up until now. Okay. So in particular, let's go back to this plot here where I have kind of many atoms. I shine in light. And my claim is that the interaction efficiency gets scaled linearly in the number of atoms. So kind of heuristically, where is that kind of argument coming from? Well, it's kind of coming from the thought that a photon coming in is a little bit like a tennis ball, right? So it's a kind of particle, has a chance to hit the first atom. If it misses, then it has a chance to hit the second atom, and so on. And so the total probability that it hits something is just scaling with n. But the point is, of course, in terms of some things, it's correct to think of a photon as a tennis ball, in terms of energy quantization. But in terms of light propagation, a photon actually propagates as a wave. So this kind of tennis ball picture completely misses the physics of multiple scattering of light, of wave interference, et cetera. Okay. So in particular, and I'll get a little bit more into this later on, the theory that led to this prediction essentially somehow in there threw out some key tenets of optics, whether it's classical quantum, which is that light is a wave and waves interfere. Without going into details, the kind of key assumption that's built into kind of standard theories, if you want, is that if I have an excited atom, then that thing is going to emit into 4 pi at a fixed rate, independent of what any other atom is doing. So it's like each atom sees its own independent path. And classically, I think we can all accept that something like that can't be true. If I have a classical system of radiating dipoles or light scatters, I know that in the far fields, I should have interference which dictates my total radiated energy or intensity. Okay? So if you take like a classical picture, the only way for that to be kind of consistent in this kind of quantum mechanical language is that the kind of spontaneous emission or photon loss into 4 pi is not independent emission. It actually has to be some form of correlated dissipation. Okay, so the point is that the previous picture ignores wave interference. And then the true kind of model somehow must involve correlated dissipation rather than independent dissipation. And now once the emission is correlated, it potentially becomes a resource. Correlated dissipation can actually build up entanglement where you didn't have it before, as an example.
Darrick, for these experiments with these numbers, can you give us a sense, which atom, which transition?
Yeah, so
how are they holding it in space, et cetera, et cetera?
Yeah, so so in terms of what atom, I would say to lowest order doesn't matter. And the reason is because these arguments here just rely on the fact that a point dipole emits a low radiation pattern of 4 pi. So actually in that sense, it doesn't matter whether you take a kind of bright transition or a narrow transition. There can be kind of technical reasons that you want one or the other, but in some sense, this is kind of independent of that choice. Now in terms of, so here I was trying to be vague because these are kind of mixing different systems together. The best quantum memory happens to be just in a cold atomic cloud. So these are atoms which see a kind of very, very broad trap just to make sure they're not flying completely randomly. But other than that, they're kind of moving randomly with at a slow velocity within this kind of broad trap. This photon gate, there's different ways to do it. The state-of-the-art one, this 50%, which I mentioned here, that's actually a small atomic ensemble inside an optical cavity. And they've further tried to enhance the kind of nonlinear interaction by going to Rydberg state. So you shine in a photon, you try to convert that photon up to a Rydberg state, which then tries, has some effect on all the other atoms and their optical response. So yeah, there's not a kind of unique way to do things. But these numbers, I think the point is no matter how you try to do it, up to now, these are the best numbers that people can get.
Thank you.
Okay, so now we can ask, how might we, take advantage of something like correlated dissipation? And so the point is that, kind of historically, people used atomic gases, so maybe even kind of, atomic vapors, which are very high temperature, so atoms are kind of constantly moving around, they're dilute, etc. And then you could kind of expect that maybe kind of correlated dissipation or wave interference just kind of gets washed out, at least in a time average sense. But the beauty about kind of atomic physics today is that now we have the technology to really kind of place atoms where we want, things like optical lattices, tweezer arrays, etc. And so what you might imagine is that you can try to take advantage of correlated dissipation just by kind of putting atoms exactly where you want to kind of use destructive and constructive interference of light to your advantage. So a kind of classical analogy in a completely different domain would be something like a kind of phased antenna array. Okay. So one possible thing that you can do is for example, try to put atoms in a dense array. So maybe it's not surprising that when you have kind of periodicity, the effects of constructive and destructive interference can be very strong. And also, when the distance between atoms becomes kind of sub-wavelength. And then one thing that you might imagine is just kind of a general strategy is, well, now when I shine the light in, maybe I can kind of exactly tailor the emission so that into the good mode, my collection efficiency, let's say into a Gaussian mode, kind of scales linearly with n. That's the same case as when you have completely disordered atoms. But maybe this kind of 4 pi emission, which I don't want, maybe I can suppress it with atom number. And it turns out in some cases, maybe you can actually even suppress it exponentially. So now if I think about the key figure of merit as being kind of a branching ratio of information, now the ratio of good or bad is scaling very, very quickly as a function of atom number. And so if I kind of try to implement this picture here, you would say that this is kind of a way to implement an efficient atom-wide interface. Should we keep going here? So there's another thing that, another kind of paradigm in which you might use systems like, dense arrays. So for example, I could have, this kind of dense array. And, maybe I have some kind of excitations or photons inside. But basically through kind of destructive interference, no matter how these excitations try, they can't find a way to escape. So I never actually have a spontaneous emission or dissipation event. And so here I can kind of, build up entanglement. Or, indefinitely. Or at least that's the kind of goal. This you might kind of call subradiance, if you want to connect it to, historical words. Okay. So I mentioned subradiance here. A lot of you in the audience, even if you don't work in quantum optics, maybe have heard of the ideas of superradiance and subradiance. These ideas are actually quite old. They're pioneered by Dickey. So the point is that the concepts are not completely new. But I think the point is that the kind of context that we have to think about, subradiance now is completely different than when Dickey was thinking about the problem. So actually, when Dickey kind of studied his original superradiance problem, he really just kind of considered an artificial situation where you have n atoms all sitting on the same point, which of course is kind of hard to do in real life. And therefore, they kind of talk equally to just one effective, single electromagnetic mode. That's not the case in kind of real extended systems. But what we can try to do now is kind of review these ideas, or rethink these ideas of subradiance and selective radiance, if you want a kind of more modern context. So let's try to bring in all the tools or ideas that we've developed in the past decades about in fields like modern quantum optics, quantum information theory, many-body physics, non-equilibrium quantum systems, etc. So the idea is to apply a new toolbox to, in some sense, this very old problem. Okay. So now let me at least try to give you a flavor of the theory of how we might think about these systems. So if you don't work in quantum optics, you might think that, well, atoms and light sounds pretty fundamental. For example, the hydrogen atom is just a textbook problem that you can solve exactly. So can we just go and solve problems like this exactly? And the answer is no. So a real system has a lot of complexity beyond just one hydrogen atom. So if I have a collection of atoms, I could easily have 10 to the 4 or more atoms. And if they're, if a lot of them are excited, then the dimension of that Hilbert space is 2 to the 10 to the 4. Right? And then you have the photons. So the point is here I'm thinking about extended systems. Weight of interference means I want to think about every single direction. So photons can be propagating in any direction. They can have any frequency, any polarization. And so the dimensionality of the photon Hilbert space, even if I have just one excitation, is already infinite. It's a continuum. Okay, so clearly I'm not going to be able to solve this generally in a kind of tractable way. So we have to start making assumptions. And for whatever reason, historically in quantum optics, the assumption that people made is, well, I'm thinking about it as an optics problem. So let me try to kind of get rid of the atoms or treat them as being secondary. In classical optics, we say, well, material is just a refractive index, right? And then we write down field equations, Maxwell's equations for the field. Okay, so that's what people kind of historically did. But then the problem is so then when you just say the atoms, I'm going to smooth them out, you get rid exactly of the problem that we want, which is this wave interference, right? Because wave interference depends exactly on where the scatters are located. So we're just kind of historical accident, I guess, that people kind of threw out wave interference. So what are we going to do differently? Okay, so in the past, if they threw that thing out, and that doesn't seem to work, then the only thing we can do is, let's throw this thing out. So let's throw out the photons. So as we saw, it's weird. I'm going to solve quantum optics by saying, well, the optics actually doesn't even matter. So let me actually kind of argue or give a cartoon picture to illustrate that that's not kind of as crazy as it sounds. So can we actually get rid of the photons and get a sensible theory? So let me just start with a kind of classical equation, which I think you'll all agree with, which is that if I have a collection of scatters or emitters, then the total field at any observation point at any time, so this is here is a total field, is a coherent sum of what I send in. So this is the input, plus the contribution which is scattered by all my elements. Okay? So the total field is the input plus the scattered field. And in the case of kind of point-like objects, I can express that as some kind of electromagnetic Green's function. So I have a point source at position rj, and I propagate that point source out to a position r. So in free space, this just encodes the kind of dipole low radiation pattern. And then I have it's a kind of classical dipole moment, like an oscillating dipole. And the field depends on the dipole at a retarded time. Okay? So actually, you see that getting rid of the photons, at least at the classical level, is completely easy. I just told you what the answer is, or at least formally. And now the point is that when you think about atomic systems, we can do the following. So my point is that quantum fields propagate exactly the same way as classical fields. So if I want in the kind of quantum case, I just have to put operator hats on all these things, and I'm done. So now I have a quantum. I've already have the formal solution of the total quantum fields. In the case of atoms, this kind of quantum dipole moment just becomes the lowering operator of this two-level system. And then the next simplification, which is really special to atoms, is that I can ignore retardation. So what that means is that if I take a typical excited atom, the length of, so it'll spontaneously emit a photon, but I convert that time of the photon to a length. That length is usually a few meters. Okay? And that sets the scale to say whether I'm retarded or not. So as long as my atomic cloud is not kind of a few meters in extent, essentially from the atomic dynamics, everything looks instantaneous. So this formally says that all the interesting content of quantum optics is only there because I have atoms or quantum scatters in the first place. If I had vacuum, then quantum optics would be reduced to kind of one-line equation in the book. Okay. So now, if I want to actually figure out the total fields, I have to figure out what the atoms are doing. You can imagine I can write down a Heisenberg equation of motion, where the kind of spin of atom J is driven by the total field that it sees. For the total field that it sees, I can just express in terms of the other atoms through this equation here. So basically what I'm saying is that you can reduce all the effective dynamics to an atom-only equation of motion, or atom-only kind of master equation or density matrix. So let me kind of just sketch out what that equation looks like. And hopefully, the form of it will be kind of intuitive. So I have a density matrix that describes the reduced system of the atoms. And I can have some combination of coherent interactions as described by Hermitian Hamiltonian. And some dissipation. So what's this coherent Hamiltonian? So the form of the interaction from the standpoint of the spins will be sigma plus, sigma minus. Hopefully that kind of makes sense. So this is exactly what photon emission and reabsorption would do. One atom is excited, it's going to emit a photon, so it lowers itself. That photon can then propagate from atom J to another atom I, which can then excite. And then the amplitude of the interaction depends on the Green's function, which is how a photon propagates from one atom to another. And then we can also write down this kind of dissipation term, The specific form doesn't really matter. The only thing that I want to point out is that the dissipation depends on correlation. So it depends on pairs of atoms. And it's that correlated dissipation, my claim is that correlated dissipation, which exactly encodes the effects of wave interference, which weren't there in the kind of conventional theories. Okay. So once I've gotten to this equation, I hope that I can at least kind of intuitively argue what the blueprint or the program for many-body quantum optics is going forward. Okay, so what we see is that atom-light interactions and importantly, including things like wave interference and multiple scattering, they're really encoded in a set of equations that looks nothing like an optics problem at all. Okay, so atom-light interactions are encoded in a spin system with a few unique ingredients. Okay, so first of all, I'm primarily interested in out of equilibrium dynamics rather than kind of ground states in general. And that's because, if I have a collection of atoms, they're going to start in the ground states, the electronic ground states. If I don't shine in light, then nothing's going to happen anyway. Okay, so I have to throw in light, at least initially. It's a kind of many-body spin system. At least kind of abstractly, even if I look at the coherent part of the interaction, it looks like a long-range XY spin model. I generically have long-range interactions because protons propagate kind of everywhere. So an atom J and atom I, even if they're far apart, can still see each other. And I have correlated dissipation, which at least abstractly can be a resource. So of course, it's not that in quantum optics we're the first ones to ever kind of throw out these words. People, certainly have thought about long-range systems, et cetera. But I think the point is that these things really kind of come together, all together in a kind of unique way for these quantum optical systems, which maybe people haven't really thought about, at least in that combination, in other settings, like condensed matter physics. Okay, so the kind of program is that we want to understand. The interplay of these unique ingredients. We have to understand how to encode. Interesting applications or phenomena. In a way that, for example, might be kind of protected from dissipation due to its correlated nature, or even using this correlated dissipation as a resource in the first place. And then, if we want to generally talk about, many-body physics, I guess kind of implicitly a lot of people would like to find strongly correlated phenomena or emergent phenomena. And this point is kind of subtle. Or it's not subtle, but here I'm only kind of sketching out vague ideas. But I guess the statement is, somehow if you generically have long-range interactions, I think most people would kind of also generically say that long-range interactions are very mean field-ish or collective spin-ish. Okay, so somehow if we want the stuff beyond that, we want to evade or find paradigms that evade mean field behavior or just physics of big collective spins or any variation of that sort. Okay. So maybe now is a kind of Christian to just kind of summarize. So, of course, I think this is a kind of challenging program to carry out for the field. But I think it's one that's, due to this kind of unique combination of ingredients, which maybe people haven't extensively thought about before. But I think it's a kind of very rewarding and beautiful program at the same time. Because I think what this says is that if there's a route forward, if the field of quantum optics, especially experimentally, can evolve and start to do even more exciting things, the basis on which it'll be built is completely different than the bases of these kind of existing platforms, right? Because more or less in these platforms here, we just say, okay, I'm going to do my best to turn dissipation down to 0, okay? And once I'm going to use that as a resource. And I don't think in quantum optics we can necessarily do that. So if we can manage to find exciting things with these ingredients, we're not going to be copying these other platforms. But conversely, those other platforms cannot copy us either. Maybe as a kind of final statement, the motivation that I presented here was kind of personal. So I really think about real atoms in empty space. They can really emit into 4 pi. Of course, there's other systems in quantum optics where that's not the case. But the point is that, generically, when you have kind of systems, interacting with, so if you have kind of qubits interacting with kind of propagating modes, whether that's kind of photons or phonons, you might imagine that kind of if you eliminate the propagating modes, you generically get the same ingredients. So even though my focus was very kind of real atom oriented, these kinds of ideas are also, also resonate a lot with other systems. So those could be kind of like atoms coupled to nanophotonic systems, superconducting qubits coupled to microwave waveguides, NV centers coupled to magnons, etc. So again, I think the kind of goals, the questions that we're thinking about actually potentially influence a lot of different platforms at the same time. So with that, I hope that, I think with that I'll kind of conclude. I hope that gives you a kind of useful exposition to the field of many-body quantum optics. But I'm happy to answer any questions that you have. Thanks.
So is there any reason to believe they're interested in this kind of phenomena? And 2, what are you hoping for?
I think so. So yeah, unfortunately in this talk I didn't have time to actually come to examples. So specific questions, or let's say kind of examples that already exist in this kind of nascent field include situations where you can kind of shine in light, and then just from this combination of ingredients, the kind of steady state will be some kind of exotic, have exotic correlations. So this could be kind of like many body dimers where all the atoms kind of form up, pair up into singlets. Of course, this is kind of biased, but in my own work, we're trying to think about how we can use these ingredients to create, topological order, quantum spin liquids, and stabilize, topological order. So again, I think the challenge is to find more examples like that, but I'm pretty hopeful that we can.
Okay. I wonder about possible comments on, say, if we are talking about, say, physical quantum computer. There are different approaches, right? Okay, and you're, going this way. Can you compare, with what exists in this field?
With quantum computing, you mean?
Yeah.
So honestly, I personally think that systems that are based on atom-light interactions, I feel like they're kind of still far away to really think about quantum computing generally. So for example, one thing that has been shown is that if you start to take these ingredients and you start building atom arrays, then in principle, if you build a photon-photon gate, that can very quickly, the efficiency can very quickly rise to 100%. But at this level, that also ignores kind of technical details. So if you actually try to build the atom array, there's other effects that are relevant, like the atoms are not infinitely tightly trapped and so on. So you get little bits of residual error, and maybe those errors are around the level of 1%. So that seems, so I'm not necessarily an expert on all the ways you can do quantum computing, but naively, that 1% still seems kind of a little bit high to me to say let's actually do kind of scalable, quantum computing. I think what really interests me is 1% seems plenty good enough to start seeing interesting things. So if you're just interested in many-body phenomenology, et cetera, I think there's plenty of things that we can do with realistic systems that exist now or will exist in the next few years. So at least that's my kind of personal interest.
Okay, thank you.
Questions? Yeah.
So, what controls how out of equilibrium your systems are? I mean, you prepare them with some sort of initial input of photons, and you've got these atoms sitting there, and then.
So out of equilibrium, yeah. So it can mean a lot of different things. So it can mean that I'm just always shining in light and trying to look at some kind of driven dissipative steady state.
Thing, so it's,
Generically, yeah. So right, just because again, the ground state of the system is just to have all the atoms in the ground state.
right.
But I could also be interested in kind of transient, dynamics as well. I think it's just a question of, right, I mean, within any paradigm that you choose to define what does out of equilibrium mean, what kind of explicitly interesting situations or dynamics can we construct?
You can prepare these, you're saying, by.
Yeah. To some extent, yes.
Do you think there is a pathway to engineering interactions with this in a specific way, say that we are able to do 1 over r squared interactions between the particles in the ensemble by this technique?
Yeah, absolutely. Right. So again, what I literally describe here is a little bit limiting because I just really restrict it to kind of atoms in free space. But yeah, so you can, for example, say I'm going to couple either atoms or NV centers to some, structured reservoir. So I'm going to engineer the propagation of photons or photons themselves, either through waveguides or through the dimensionality of the material. With many of the systems, we also have the usual, tricks of control. So with atoms, these are totally compatible with just putting in Rydberg interactions, for example. I can also think about solid state implementations where I have kind of extons that I could have, extra kind of short range interactions coming from the extons. So yeah, in principle.
But I mean rather the light mediated part of the interaction, not by putting in extra stuff. So when you're tracing out the photons,
right.
then you get some effective model that describes your atoms, and you have some interactions to the screen functions. And is there a way how we can actually tailor this so that the interaction behaves in a certain way with distance between the
In principle, yeah. So So then that comes down to what are the so this Green's function is just a classical quantity. So basically all the kind of usual, all the tools that you have from, let's say, photonics and so on, and knowledge of how we can tailor this Green's function either through dimensionality or through special devices, photonic crystals, etc. Yeah, those are ways to manipulate G to have maybe not arbitrary forms, but to have a lot of flexibility.
When I think about nonlinear optics in a classical setting, I think about things like four-way scattering or maybe saturating nonlinearities. When you think about it in a single photon sense, is it sort of the same kind of thing plus stochastic noise, or do you have to sort of think in a completely different direction?
No, so things like these atoms, like if I take a two-level atom, I can exactly have like four-wave scattering processes. There are formalisms to go and calculate that, at least for kind of simple systems, like S-matrix techniques. So really built from quantum scattering theory. So a lot of things that you associate with kind of that can occur in the classical optical nonlinear optics domain can actually happen here. I think a general challenge is always about scaling. So if I have one atom, I can easily calculate this S-matrix, and figure out the Fourier scattering. Now if I have complexity, that all these individual photons, they generate new colors, they're bouncing around through multiple scattering. I think the it's really a conceptual bottleneck. Like, what can I predict from that would be interesting, almost given as a certainty that I cannot solve the problem exactly.
More questions? Okay, thank you, Darrick.